This video is brought to you by mywayteaching.com.
Next is heterogeneous equilibria. Equilibrium in a system having more than one phase is called heterogeneous equilibrium. Homogeneous means which is having same, all phases are same. The equilibrium between water vapor and the liquid water in a closed container is an example of heterogeneous equilibrium. Means see, water vapor it is in liquid state. In the container, but the liquid state water which is present in the liquid state, that is H2O in liquid state, right? Then which is in the gaseous state, so that is called water vapor. This is called a heterogeneous equilibria. Okay, next problem. The value of Kp for the reaction, I will write down the reaction: carbon dioxide plus C, which gives 2 monoxide, that is in gaseous state. Okay, this is solid and this is also in gaseous state. Here is 0.3 at 1000 Kelvin. If initially uh, PCO2 is equal to 0.48 bar, PCO is equal to 0 bar and pure graphite is present, calculate the equilibrium partial pressures of carbon monoxide and carbon dioxide. Okay, solution for the reaction, let x be x. Okay, for the reaction, let x be the decreases in pressure of carbon dioxide, then carbon dioxide plus 2 carbon monoxide. Initial pressure is equal to 0.48 bar, then 0. At equilibrium, 0.48 minus x bar to x bar. There, so Kp is equal to square divided by PCO2 and Kp is equal to 2x whole square divided by 0.48 minus x is equal to 3. Then 4x square is equal to 3 into 0.48 minus x. Okay, 4x square is equal to 1.44 minus x. So 4x square plus 3x minus 1.44 is equal to 0. You are getting A value 4, B value 3 and C value is equal to minus 1.44. From the equation we can write minus plus or minus root of B square minus 4AC divided by 2A. Okay, after substituting the values, square root of what is B square? 3 square minus 4 into A is 4, C is minus 1.44 divided by 2A. A is 4. So you will get minus 3 plus or minus 5.66 divided by 8. Minus 3 plus 5.66 divided by 8. So here after solving this one, as value of x cannot be negative, hence we neglect the value. So we are getting negative value, so that value is negative, so that we are neglecting it. Next, x is equal to 2.66 divided by 8. Okay, here x is equal to 2.66 divided by 8, so you are getting 0.33. The equilibrium partial pressures are the equilibrium partial pressures are PCO to x is equal to 0.33 is equal to 0.66 bar 0.48 minus x is equal to 0.48 minus 0.33 is equal to 0.15 bar. Okay. Next concept is applications of equilibrium constants. Okay. What are the applications of equilibrium constants? See, equilibrium constant is applicable only when concentration of the reactants and the products have attained their equilibrium state. Both here concentration of reactants and products should be have attained their equilibrium state. Next, the value of equilibrium constant is independent of initial concentrations of the reactants and products. The value of the equilibrium constant. Equilibrium constant means Kc. You know about it, Kc. Okay, so initial concentration of the reactants and the products. Next, equilibrium constant is temperature dependent. Uh, okay, having one unique value for a particular reaction represented by a balanced equation at a given temperature. Next, the equilibrium constant for the reverse reaction is equal to the inverse of the equilibrium constant for the forward reaction. The equilibrium constant for the reverse reaction is equal to the inverse for the equilibrium constant for the forward reaction. And the next is the equilibrium constant K for a reaction is related to the equilibrium constant of the constant of the corresponding reaction whose equation is obtained by multiplying or dividing the equation for the original reaction by a small integer. Okay, the equilibrium constant K for a reaction is related to the equilibrium constant which is in continue, that is related is equilibrium constant. I will write down here of the corresponding reaction. Okay, so these are the some applications of equilibrium constant. Note down these five equilibrium constant applications. Okay, and next topic I will cover. Okay, next topic is predicting the extent of a reaction. Okay, what is meant by predicting the extent of a reaction? You know, the numerical value of the equilibrium constant for a reaction indicates the extent of the reaction. The numerical values the numerical values of the equilibrium constant for a reaction indicates the extent of the reaction. Numerical values of the equilibrium constant for a reaction indicates the extent of the reaction. But it is important to note that an equilibrium constant does not give any information about the rate at which the equilibrium is reached. It does not give any information about the rate, okay, when which the equilibrium is reached. The magnitude of Kc and Kp is directly proportional to the concentration of the product. Let's see, Kc and Kp, which is directly proportional to the concentration of the products. Okay, so this implies that a high value of K is suggestive of a high concentration of products and vice versa. Okay, so this is predicting the extent of reaction. And next is predicting the direction of a reaction. Consider now, uh, when before going to this, just consider the general equation. You know what is general equation? That is AA plus BB. Okay, okay, so QC is equal to divided by, okay, so then after considering this general equation, now QC is greater. If QC is greater than KC, KC is nothing but equilibrium constant. Okay, and what is Q? The equilibrium constant helps in predicting the direction in which a given reaction will proceed at any stage. For this purpose, we calculate the reaction quotient, where Q is called reaction quotient. The reaction quotient QC with molar concentration. QC means where QP is partial pressure, is defined in the same way as the equilibrium constant Kc, except that the concentrations in Qc are not necessarily equilibrium values. So now you know what do you mean by Qc. Qc is a reaction quotient. After that, if Qc is greater than Kc, the reaction will proceed in the direction of the reactants, means in the reverse direction. If Qc is less than Kc, then the reaction will proceed in the direction towards the product, so forward reaction. If QC is equal to KC, the reaction mixture is already at equilibrium. Okay, and next is um, problem. Okay, this one is predicting the direction of a reaction. Next, consider the problem. The value of Kc for the reaction, I will write down the reaction here. 2a B plus C is 2 into 10 raised to minus 3. At a given temperature, the composition of reaction mixture ABC is equal to this much, 3 into 10 raised to minus 4 molar. In which direction the reaction will proceed? Okay, consider the solution. Now, we know that the reaction quotient, when we are considering the concentration QC is equal to B C divided by A square. We know that as A is equal to B is equal to C is equal to 3 into 10 raised to minus 4 mole. So that QC is equal to 3 into 10 raised to minus 4 and C is equal to 10 raised to minus 4, same value, and A is also 3 into 10 raised to minus 4 square. So this one cancels, so you are getting value 1. As QC is greater than KC, So the reaction will proceed in reverse direction. Okay, next, calculating the equilibrium concentration. So first one is step 1. First, while calculating the equilibrium concentrations, write the balanced equation for the reaction, the first step. Next, second is, under the balanced equation, make a table that lists for each substance involved in the reaction. Make a table that lists for each substance involved in the reaction. The first one is A, the initial concentration. The initial concentration. Second one, the change in concentration ongoing to equilibrium. The change in concentration on going to equilibrium. And C, the equilibrium concentration. Concentration. In constructing the table, define X as the concentration of one of the substances that reactants ongoing to equilibrium. Then use the stoichiometric of the reaction to determine the concentration of the other substances in terms of X. This is step 2. Next, step 3. Substitute the equilibrium concentrations into into the equilibrium equation for the reaction and solve for X. And the next, if you are to solve a quadratic equation, choose the mathematical solution that makes a chemical sense. And the next fourth step is, calculate the equilibrium concentrations from the calculated value of X. And the last step, fifth step is, check your results by substituting them into the equilibrium equation. Okay, so this is calculating the equilibrium concentrations.